Electricity. It is a form of energy that helps us to a high extent in our daily life. Our society can never think about a state without electricity. Electricity has influenced our life to such a great extent. We make use of electricity to operate a mixer, to lit bulbs, to operate machines, to run trains, etc. Haven't you seen distribution lines going overhead of us over towers in different directions? Do you know that these lines are energy carriers? We can definitely say that these are landmarks in the progress of humans. Do you remember having learned how electricity is produced? Is it not by making use of electric generators? Do you know from where all are we getting the energy required for driving these generators? You might have seen generators of different sizes working in shops, houses, etc. But the generators used in cinema theaters, convention centers, etc. are of a bigger size. But we cannot say that these are power stations. Do you know from where are we getting the mechanical energy needed to run the generators used for the commercial production of electricity, which is on a very large scale? Based on the mode of supplying mechanical energy for generators used in power stations, we can classify the power stations as hydroelectric power stations, thermal power stations, and nuclear power stations. Hydroelectric power stations. Take a look at this. This is the Idukki Dam, the prestigious dam of Kerala. This is an arch dam which is ranked very high in the size. Here you can see a power station in which the water flowing down is made use for driving turbine with a generator which is made to work for the production of electricity. Such power stations which make use of flowing water for the production of electricity is referred a hydroelectric power station. There are several hydroelectric power stations in Kerala which are large or small. The water stored in a dam under very high pressure is made to flow down through pipes known as penstocks. There are valves and other complicated technical devices to control this water coming down under pressure. Using the power of the water flowing down through penstocks, huge turbines are made to rotate. What is the energy changed happening here? The potential energy of blocked water changes into kinetic energy and then into electrical energy. The rotating turbine is attached to electricity generators. In these generators, mechanical energy changes into electric energy. Thermal power station. In a thermal power station, fuels like naphtha, coal, etc., are allowed to burn to produce heat. Using this heat, water is boiled to get superheated steam under high pressure. Using this power of steam, turbines are rotated. In our country, thermal power stations are being operated in Neyveli, Kayamkulam, Ramagundam, etc. Take a look at the energy changes happening here. The chemical energy of water changes into heat energy, then into mechanical energy, and at last into electrical energy. The major problem of a thermal power station is the environmental pollution. Nuclear power station. This is the third variety among power stations. Here the fuel is nuclear energy. By making use of controlled nuclear fission, heat energy is obtained. Using this heat, water is boiled to get superheated steam under high pressure. Using this power of steam, turbine is rotated. In India, nuclear power stations are being operated in Tarapur, Kalpakkam, Kodamkulam, etc. The nuclear energy changes into heat energy, then into mechanical energy, and at last into electrical energy. Nuclear power station is the one which needs utmost care. Power transmission is the process of sending electricity from the place where it is generated to the places where it is consumed. The wires or strings used for the purpose are the transmission lines. Using conducting wires and very high towers, electricity is transmitted. Take a look at the transmission line passing over hills, rivers and fields, etc. There are different stages in power transmission. The first stage is increasing the voltage many folds. Voltage loss and power loss are the two main problems in power transmission. When electricity is passed through a conducting wire, a part of it is lost in the form of heat. This loss increases with increase in the length of the transmission line. There are two methods to minimize this loss. One method is to reduce the resistance. You have learned that the resistance can be reduced by increasing the thickness of the wire. But this is not practically possible beyond a limit. As the thickness of strings increases, the weight of the strings also increases. It increases problems due to difficulty in supporting the heavy strings, technical difficulties, etc. The second method to reduce the loss is to reduce the current. You know the relation P equals VI. Here I equals P divided by V. If the voltage is enhanced 10 times, current will be lowered to 1/10 and heat to 1/100th. Try to give numerical values in the formula and calculate accordingly. For example, if P equals 1000 watts and V equals 100 volt, then I equals 10 ampere. If the voltage is made 10 into 100 equals 1000 volt, then the current equals 1000 divided by 1000 equals 1 ampere. If the voltage is enhanced 10 times, current will be lowered to 1/10th. According to Joule's law, the relationship between heat and current is H equals I squared RT. By how much will the heat decrease if the current is decreased by 1/10th? Is it not by 100th times? Now you might have realized the need for transmitting electricity at a very high voltage. In any power station, electricity is generated at 11 kV. This is raised to 220 kV in the first stage. It is this electricity at very high voltage that is being sent using lines over towers. The second stage is lowering the voltage. In the substation, at the second stage, the voltage is reduced to 110 kV, 66 kV, 33 kV or 11 kV using step-down transformers. Electricity is given to major industries from this substation. Electricity is sent at 110 kV to the next substation from here. In the third stage substation, the voltage is lowered to 11 kV using step-down transformers. From here, electricity is given to small-scale industries at 11 kV. Aren't we using 230 volt for domestic purpose? The step-down transformers in the fourth stage converts 11 kV into 230 volt. Now you might have realized the need for the use of step-up and step-down transformers in power distribution. If power production fails in any power station, then the area which receives electricity from that substation will be suffering due to lack of electricity. But there are methods to overcome this problem. This is achieved with the help of power grid. Power grid is the network arrangement for interconnecting different power stations and distribution systems. Due to this interconnecting network, we can make electricity available at any place if there is an additional demand or if there is a failure in power stations. Haven't you heard about power cut and load shedding? These are the arrangements executed when there is insufficiency in electricity. For industries, electricity is normally given to a certain limit. When there is shortage, a definite percentage of this allotment is cut off. This is power cut. When there is deficiency of water in dams, all generators cannot be made to work at the rate in which they are working. If so, electricity will not be available for distribution. In this case, we will control the flow of water and control the working of generators. Whenever there is shortage in the power production, the supply of electricity in certain region is blocked for a definite interval of time. Different areas will be blocked at different intervals of time. If so, in the regions where electricity is being supplied, sufficient electric power can be made available. Such an arrangement is known as load shedding. Use electricity judiciously. Never waste it. Switch off fans, bulbs, etc. whenever you leave a room. Each unit of electricity is precious. Save it and limit the use of it. Replace filament lamps by CF lamps or LED lamps. What else can be done to avoid the wastage of electricity? This is a step-down transformer which lowers the voltage of electricity reaching us from 11 kV substation to 230 volt. Through how many lines is electricity reaching this distribution transformer? Is it not 3? But how many lines are there in the output? There are 4 lines. Let's see why is it so. For this, we should know what delta connection and star connection are. In all the stages of distribution of electricity from the production center, the windings in all the transformers are in delta connection. Here you can see the sample of connection of coils in a delta connection. When connections are made like this, there are 3 phase lines. There is no neutral line. In transformers used for power supply to factories and many industries, there is a delta winding in both primary and secondary of transformers. Most of the electric motors are in need of 400 volt. For distant transmission, we make use of delta connection since we need only the 3 lines. The input of a distribution transformer is in delta winding. Hence, 3 lines alone are reaching a distribution transformer. But the output is in another form which is known as star connection. Take a look at the sample of this. There are 3 phase lines and a neutral line in star connection. From such a connection, we can avail electricity at both 230 volt and 400 volt. The potential at the point where the 3 coils meet is 0. The line taken from this point is the neutral line. The potential difference between any 2 phase lines is 400 volt. Why is the potential difference between any 2 phase lines 400 volt and not 460 volt? Let us see. In the figure, angle A and B equals 1 by 2 into 120 degree equals 60 degree. The potential difference between any 2 phase equals AB. Consider right triangle AND. Sin 60 equals AD divided by AN. AD equals AN sin 60 equals 230 root 3 by 2. AB equals 2AD equals 2 into 230 root 3 by 2 equals 230 root 3 equals 230 into 1.73. That is equal to 398.36, approximately equal to 400 volts. The potential difference between any one phase line and neutral line is 230 volt. Domestic connections are given from any one phase line and neutral line. The potential difference between earth and neutral line is 0 volt. Now let's see how the domestic circuits are made. Take a look at series connections and parallel connections. This is a series connection. When connections are made like this, the effective resistance goes on increasing with increase in the number of devices connected in the circuit. All devices will not get the same voltage. The applied voltage is shared. Devices will not get required current. We cannot control devices individually using switches. Now take a look at the parallel connection. This arrangement is made use of in domestic connections. What are the advantages of this type of connection? We can control devices individually using separate switches. All devices will get the same voltage. Each device will get required currents. Each device will work according to the power marked on it. This is the model of an electric circuit arrangement in a house. The connecting wires coming from phase line, also known as live line, and neutral line are directly connected to the watt-hour meter. which is a device to measure the electrical energy consumed. Then the phase line reaches the main fuse. Then the phase line is connected to main switch. The neutral line reaches the main switch directly. The main switches are connected to control the electricity for the entire home. There will be earthing from main switches. Then the connection reaches MCB, that is the miniature circuit breaker. From here, different branches are taken for various rooms and halls. See how the electric connection in a room is made parallel. For certain devices like electric iron box, 3-pin plugs are used. This is to ensure better safety. The earthing pin in the 3-pin top is thicker and longer than other pins. The pin is made longer to ensure that it gets connected first while inserting the 3-pin top into the socket and gets disconnected at last while removing. 3-pin is used to ensure that a person operating the device will not get electric shock if the phase line comes in contact with the outer metallic cover. If electricity reaches the metal cover, it flows into the earth through the earthing wire. High current flows through the wire since the resistance of the wire is very low. This increases the heat developed in the fuse wire. Hence, it melts and breaks the circuit. Thus, it ensures better safety. Haven't you understood the need for proper earthing and the use of proper fuses? Electric energy is measured in the unit kilowatt-hour, which is popularly known as unit. A device of power 1 kilowatt, that is 1000 watt, uses 1 unit energy in 1 hour. We can make use of the formula energy consumed equals power in watt into time in hour divided by thousands. Suppose a TV of 100 watt is used 5 hours a day. 6 fans of 60 watt each are used 8 hours a day, and 7 CF lamps of 20 watt each are used 5 hours a day in a home. Let us see how much energy is consumed in a day. Energy used by TV equals 100 into 1 into 5 by 1000 equals 0.5 kilowatt hour equals 0.5 unit. Energy used by fan 60 into 6 into 8 by 1000 equals 2.88 kilowatt hour or 2.88 unit. Energy used by CF lamps